Hello, everyone. Welcome to Pre-Lecture 21. This is going to be our second and final lecture covering Chapter 15. So last class, we introduced the concept of a solubility product and equilibrium that may exist between a solid and a partially soluble salt and its dissolved ions. And in this class, we're going to try and expand upon that a little. So if we think about our solids, such as silver iodide here, that dissolves into silver and iodide, of course, if it dissolves in pure water, then we only need to worry about how much of each of these would be dissolved, which would, of course, be determined by our KSP expression. However, say we have a solution that has a common ion with this, and so say that solution, instead of being just pure water, had another species, such as sodium iodide. And sodium iodide is, of course, fully soluble. And the presence of additional iodide in our solution would decrease the overall solubility of our silver iodide species. And we could, of course, prove that if we were to put this into an ice chart and solve for how our equilibrium would be affected with the presence of some additional species. And so we will do that in class, but just wanted to introduce the concept right now. And here is a conceptual question for the common ion effect. And so of these four choices here, which of the species below would decrease the solubility of magnesium hydroxide? So if you want to take a moment to think about that, you can do that. And then I will show the answer here in 1 second. And so it would actually be A and B, and that is because when we add magnesium chloride, some of that, if not all of that magnesium chloride, in fact, would dissolve and would, of course, be contributing to the presence, the common ion of Mg2+. And if we dissolved potassium hydroxide, then we would have a greater concentration of hydroxide from the KOH that would contribute to a lesser solubility for magnesium hydroxide. One of the tricky ones is MgOH2. So if we had magnesium hydroxide and we add more solid magnesium hydroxide, then the concentration of our dissolved species is not going to be affected, right? Anytime we have these solubility products, anytime we're measuring the concentration of the species at equilibrium, that is in a saturated solution. And so adding more magnesium hydroxide solid would not affect the concentration of magnesium nor hydroxide that was already dissolved, okay? All right, shifting gears a little bit. So that was common ion effect. This was a slide from, I believe, our first lecture of chapter 14. I believe it was lecture 15, talking about the different definitions for acids and bases. And so up to this point, we've been primarily dealing with Arrhenius and Bronsted-Lowry acids and bases, but we of course also have Lewis acids and bases. And so as a reminder, Lewis base can donate an electron pair, whereas a Lewis acid will accept or receive that electron pair. And so it's a restatement of that definition. If we were to look at chemical examples of Lewis acid-base complexes, we could have something like aluminum chloride here that does not have a lone pair, but has an orbital capable of accepting a lone pair from ammonia and H3, and so they would form that bond there. Another example could be boron. Any sort of boron compound is kind of notorious for forming or acting, I guess, rather, as a Lewis acid, where it will accept an electron pair, in this case from a molecule called diethyl ether, to form this boron trichloride diethyl ether adduct here. So again, we just have donation of this electron pair from our ether into our boron, okay? The reason I bring this up is one other form, I believe our last form of equilibrium we'll be talking about this semester are called, or are related to complex ions. And in particular, the equilibrium of the formation of those complex ions, which we've also called coordination complexes in lab. Okay, and so they consist of generally a metal at the center and then one or more ligands bound to that central metal. And so the metal acts as a Lewis acid, which accepts our electron pair, and ligands will be our Lewis bases that donate those. Okay? And then just another thing to know, of course, the number of ligands bound to that metal is the coordination number that we would say of the metal. So if we think about this in terms of equilibrium, say we had our silver ion, so Ag plus, that's soluble. If that were to react with two equivalents of ammonia and H3, it could form this complex ion that we'd call silver amine right here. And of course, as always, we can measure an equilibrium constant by taking our products over our reactants. So we have our soluble product here, that's our complex ion, divided by our reactants, which it looks like I forgot a bracket there, but that squared should be, of course, for the concentration of ammonia. In this case, the formation constant is 1.7 times 10 to the 7th. Okay? And typically, these formation constants tend to be quite large, so much greater than 1, typically on the order of 10 to the 6th or above. Okay? And so this can be very handy when we have some sort of cation, a metal that will form a complex with other ligands, and it will make it more soluble. So if we consider another silver salt, silver chloride, that is partially soluble, we have a KSP value of 1.6 times 10 to the minus 10th. If we were to add in ammonia into this solution, we would form our silver amine complex, which we just determined the KF for that is 1.7 times 10 to the 7th. And for the coupled equilibria, we can determine an overall equilibrium constant by multiplying these two K values together. So KSP times KF would be equal to these two quantities multiplied together to get a total value of 2.72 times 10 to the minus 3rd. So we're still not favoring the overall products of the reaction, but our silver would be a lot more soluble in the presence of ammonia as compared to if we had just silver chloride in pure water, right? Okay, there's also a chart I included here. Should you ever need to reference this, this is just formation constants for different sorts of atoms that we have. And I may reference this in class again, but I would of course provide any of these values should you need them for any sort of example that we go over in class. Okay. Right. I hope you have a wonderful day, and I will see you in class on Tuesday. Take care.